understand the thing.
เรามีโมเลกุลหนึ่ง
Say again, what is the question?
ซึ่งเราคิด
จูจู
น้ำเนี่ยแหละ
ไปถามเขาเลย
ก็เหมือนเรา
ถ้าให้ฉันถามเหรอ
เราอยากรู้ว่ามันเป็นน้ำ
ฉันถามเหรอ ถามอะไรอ่ะ
เรื่องที่แกบอก
สามารถบอกได้ว่า
ช่วยกับ
ตรงเนี้ยมหาวิทยาลัยข้างในมันเป็นเท่าไหร่ตรงนี้แบบการขยับในแต่ละในแต่ละอันอะเป็นดิ้งที่จะมันจะมีมันจะมีดาต้าเบสมันอยู่ว่าถ้าสมมติว่าโอ้เนี่ยขยับแบบ
อันเนี้ย symmetry เนี่ยsymmetry สองอันเนี่ย wavelength มากกว่าใช่ปะ
แต่เมื่อตอนเนี้ยถามเองเนี่ยจริงๆก็ถามมาแล้ว
symmetry wavelength มากกว่า
Are you sure?
เนี่ย582ยังไง2919
Asymmetry is higher, have higher wavelength than
Higher frequency, not higher frequency, higher energy. Usually as a rule of thumb.
yeah, higher frequency and higher energy. Yes.
โอกับเพศเหมือนกันอะไร
ทำไมอยากถามว่า
It vibrates faster.
yeah,
No, this one is just faster than this one. Not very much, but a little bit. And the lowest is the bending, yeah. The bending is only about half as fast.
ถามอะไรเพราะเราจะถาม initial ถ้าเข้าใจ initial condition ไหม
คุณอยากถามว่าอะไรคืออยากถามว่าอะไรก่อน Initial condition
potential energy
ฉันอยากถามว่า initial condition เหมือนจากการที่เรา
Hopping,
เหมือนสโคปมาบอก
or coupling.
เรา
Okay, we just, I mean, potential energy coupling, what we call it just a word, is this
ประมาณว่า
off diagonal elements.
คือเขาจะอย่างเงี้ยเขาจะแบบคิวเราได้คือว่าเป็นกลม
Look, if I look at Michael's force constant matrix,
เราหาเองเท่ากับ
so here I have OH stretch 1. Here I have OH stretch 2.
Yep.
Here I have HOH bend. Okay? Now this matrix, so Michael wrote some numbers here. Here it was 8 point something. Here it was 8 point something. And here I don't know what it is, 2 point something. This is a way to write the harmonic potential energy surface. He called it force constant matrix or force matrix.
ไอตัวไอสันนิษฐานเรื่องเป็นเรื่องของเอกไวแซ
ข้างในเป็นตัวค่าของ
Okay? So if you write this as a matrix, it means you will want to multiply it with a vector. So let's say I have here the vector OH1 stretch, OH2 stretch, bend. And here I have the same vector, but here I have to write as a row, formally for
แต่ว่าคือ
mathematicians.
energy ที่เก็ตมา
OH1, OH2,
ที่รอบที่มันใกล้ๆจะเข้าสู่
So if I make you know how to multiply matrix with vector, okay? So this times this plus this times this plus this times this, and then this times the result. It will give, if I do the multiplication, it will give that potential energy is 8 point something something
ได้นั่นแหละมันต่างกัน
ROH1 square plus H ROH2 square plus
ไม่รู้นะรู้แต่ว่ามันจะคง
2 times bend.
มันขึ้นอยู่กับความละเอียดด้วยไง
So this you recognize, right? This is just one spring for OH1 bond, another spring for OH2 bond, and one spring for the angle. So this writing is exactly the same as this writing. Right? This is just better for the computer to write like this than to write like this. Okay, and this we would call diagonal, right? Because we have numbers here only in the diagonal. Okay? Now if you look how these normal modes are computed, you see that you can also write numbers here. And usually it's maybe a small number. I think it's small and negative here. Okay, so I can write the number here, and the matrix is symmetric, so I have to write the same number here. What does it mean?
อ๋อจะเป็นฟอสไง
Well, if you do the product again, you will see that it means minus 0.1 ROH1 times up
เปลี่ยนหมด
times ROH2. And this one is called coupling, exactly.
แต่คือที่ผมมาเรียนรู้เนี่ย
Because you see, here it depends only on one, here it depends only on two, and here it depends on both. So this is what I would call potential energy coupling. And these three that can appear here,
อ๋อโอเค
they are called the potential energy coupling constant or just coupling constant. So this would be potential energy. Now, if you do the calculation, you find that even if this is zero, so even if I put all this zero, so I have only diagonal force constants, I will find that the solution is asymmetric and symmetric. So even though here, this is not there, they know nothing about each other in terms of potential energy, and this is potential energy, right? Even though they know nothing about each other, in the potential energy, in the movement they know each other because of kinetic energy. And essentially, as Michael said, because you want to keep the center of mass constant, you do not want, okay? And so it's just to have this condition of center of mass not moving, that you have this other coupling. And since this one is called potential energy coupling, the other one they just call kinetic energy coupling. Okay? So it's really because of the motion, right? Because you want the motions to be such that the center of mass does not change. Okay? I can tell you one thing, many colleagues of mine have not understood this. I've explained it to many colleagues. You know who I mean. So this is not so easy, and in particular when you do experiments to identify what is what, that is not so simple.
Yeah.
And this is why people use isotopic substitution, because you see these things here, whether here I write OH or I write OD is the same thing because of Born-Oppenheimer approximation. Because this is just an approximation to the potential energy surface. And the potential energy surface, that depends only on the electrons, and so it must be the same for different isotopes. Right? Isotopes, just mass different, but you know, same number of protons, same number of electrons, so same electronic Hamiltonian, so same wave function, same electronic eigenvalues. So this does not depend on the mass, on the isotopes. But the motions depend. You know, remember the dance, the motions depend on the mass. But again, these normal modes, they are only a very, very simplified case, because I look only at the very, very bottom of the potential energy
เรา
surface.
เปลี่ยนไปถึงแล้วก็แตก
You know, as soon as I have enough energy to move a little bit up, then it's not harmonic anymore. Then all this doesn't work.
ใช่
อะไรนะ
คือถ้าโมเลกุลนะครับมันแล้วก็มีในตัวโมเลกุลก็ขึ้นไปแล้วนี่แหละให้เอชให้เอชเพิ่มขึ้นไปเอชมันก็จะทำให้คาร์บอนต่อไป
เพราะว่าอันเนี้ยที่เราไอเดียเคสแบบมองที่อุณหภูมิไม่ถึงที่ต่ำมากๆถูกไหมที่เขายกตัวอย่าง
assume that energy is constant total energy is constant right
For the normal modes,
yes yes
you don't really look at energy. I mean, that's maybe an interesting point. You know that the frequencies are not energy dependent.
yes
You know, if you take the harmonic oscillator,
yeah
okay, if I take a harmonic oscillator, let's just think of the simple harmonic oscillator. And to make it really simple, we'll just use one glass. And now I have initial condition, so I pull, like in the gym, okay?
yep
And I observe the oscillations. Okay, let's say like this.
yes
Now I pull less. So I have less energy. Right? If the energy here, I mean the harmonic potential is like this. So if the energy here is 0, the energy is K times X squared.
yes
So if I pull a lot, then the energy will be much higher.
yeah
Okay, now what about the vibration? If I pull harder, if I start here, or here and not here, will the frequency be different or not? Yes. Only in Cambodia.
oh
No, the frequency is exactly the same. What changes is the amplitude, right? But the frequency is the same.
ที่เราพูดจากการกระทำของมันเองใช่ไหมก็เลยโยงแรงสองในการทำงาน
You never did this experiment in high school? Or pendulum, same thing with the pendulum. You know, if you have a pendulum,
อ๋อ
and it swings a lot, or it swings a little, the frequency is the same. This is when you have a clock, you know, you have these old clocks. Dong, dong, dong. No? They don't have these old clocks? Yeah? Well, you know, it's not really sensitive whether the pendulum goes like this or whether the pendulum goes like this, because the frequency is always the same. So all this normal mode business, this behaves like this. This does not, the frequencies do not depend on energy.
so the only thing
But of course, you know in real life, you know, if, so let's look again at the potential energy surface and at the harmonic approximation. So a harmonic approximation goes something like this. You see? Here, the frequency is always the same. But if you have a motion like this, it will not be the same.
yep
Right? I mean, for instance, if you have a very high energy, here it will go,
yeah
and take forever to come back.
yep
So, in an anharmonic potential, the frequency, or let's say the frequency does depend on energy, but not in the harmonic potential. Just harmonic potential. Just, we're talking only about harmonic motion.
ก็คือถ้าทำมันอยู่ potential จะเป็นเส้นกราฟสีแดงใช่ไหม
yes
แต่ของ
And
ระ
you
บบ
see,
เราไม่ใช่
I mean, you can see the harmonic approximation is very bad. I mean,
เดี๋ยว
Yeah.
if this is the real potential, if this is the real potential energy surface, then the approximation is okay. You know, maybe for small displacements. But as soon as you have big displacements, then usually the harmonic approximation is not good anymore.
กูเคยอยากเข้าใจนะเว้ยจนมาถึงตอนนั้น
So harmonic we like because it's so easy to compute,
ปีนเปีย
so it can like
but it's sometimes not very realistic.
some of them
Hmm?
so like harmonics can use to approximate them like this style
Well, remember this one picture I had? Maybe I can find it
บอกว่า
again.
ฮาร์โมนิกมันไม่ได้ดีขนาดนี้
แต่มันก็ใช้ได้บ้าง เพราะว่ามันมีส่วน
มันใช้ได้บ้างแค่ตรงนี้ปะคนก้นที่มันต่อ
ซึ่งมันก็คือตรงที่เราอยากศึกษา
ปีนไปมันได้กลิ่น
ก็เนี่ย
ติดคุยนั่งนี่หรอนี่หรอ
ไม่รู้เรื่องนะ
เดี๋ยวผมจะดูทุกคนนะ
ตอนที่ยังปรึกษาคุณที่แม่ไม่ดีจะมีวิธีการกินง่ายๆครับ
พอ
ใช่แบบน้ำมันจะมี
Ah, here it is.
แต่ว่าถ้าแต่งแก้ต้องใช้อะไรครับ ที่มันมีไปที่หนักเกินเลยน่าอธิบายผมไม่รู้นะจะไม่
Remember this picture?
อย่าง
Potential energy surface intramolecular. So for, let's say, a bond, like an OH bond, and intermolecular, like, for instance, for interaction, well, maybe hydrogen bond, or maybe just dispersion interaction. And you see that for when the potential is deep, right, then the harmonic approximation can be quite good. So typically for bonds, the harmonic approximation is okay. But for intermolecular interactions, I mean, try to find a harmonic fit for these red curves. It will not work. I mean, it will always be terrible.
Yeah.
Either it will work on the left side, it will be terrible on the right side, or maybe it works a little bit on the right side and it's terrible on the left side. You just cannot do it. Okay? So the harmonic approximation is basically, you could almost call it bond approximation. If you have strong chemical bonds, this is a reasonable description very often. But if you have weaker interactions, then usually it's not. But you know, sometimes in a solid, if you have metal, like people have used nickel a lot, I don't know why. In a nickel metal, you can describe very well with harmonic interactions between the nickel atoms. So it's a nickel spring here, spring here, spring here, spring here, and that works quite well. Okay, so it's good to keep this in mind, and also to remember that this is the same thing. I mean, this is always the electronic energy made by the electrons as a function of something, as a function of the distance. But that practically, to describe this mathematically, you use different things. I mean, to describe these green curves, you use the stretch and bend and torsion approximation, and to describe the red curves, you use maybe Lennard-Jones and Coulomb and something like that. But this is just for practical reasons. And you can find many papers where people say, you should do this and you should do that, and this is a good description. I mean, just to describe the potential energy surface of water, I suppose you can find 200 different descriptions in the literature. They're all called model. The something something model, the something something model, the something something model. They all have sort of abbreviation. TIP and TIPS and TIP4P and SPC and MCY and CF and it's all that people have tried different ideas, different thing to represent as best possible the potential energy surface of two water molecules. So whenever you see some work, people will say, we have used this and this representation. We have used TIP 5P 2005, and we have used SPC flexible, and we have blah, blah, blah. And I've also made such a representation. Has some advantages and some disadvantages. So it's not so simple. I mean, it's very simple to say, okay, this is the potential energy surface, and we get it from quantum mechanics. But to actually make it usable for solving Newton's equation, for instance, where you have to take the derivatives, that's a different business. More questions? Ja, wird sogar drinnen.
เข้ากับเพลงเศร้าอ่ะ
More questions?
No, this
Everybody happy.
This one.
I don't think so.
Like this, what you.
ไม่มีคำถามเลยอ่ะ
I mean, I can tell you for the exam, it's important that you have an overview, that you understand, yeah, the different steps. I mean,
คำตอบใช่ไหม
first do this, then do that. Take this result, express mathematically, do this, do that, that sort of thing. The important thing. Nobody is going to ask you to write down some specific matrix or whatever. That's
อ๋อ
สาม
ไอ้ค่านี้มันมาจากไหนอะเราจะหาค่าที่แบบว่าอยากได้
แต่ค่านี้เราก็ยังเชื่อมโยงไม่ได้เลยนะ
อ๋อขนาดเบนซ์เนี่ยนะ กูแตกแล้วทั้งนั้น
ไม่เชื่อมโยงไม่ได้เรายังเรียนไม่เรายังแบบเรียนยังไม่ครบเลย
she said she
อุ๊ย
don't
ตายแล้ว
understand at all นะ but she said
You don't understand the
I
whole
don't
thing?
know anything อ่ะ oh my god
I think I have to review and connect our lesson how to connect them
I mean,
ก็ใช่ถูกต้อง
maybe we should restate again the purpose. What do we try to do, or why do we do it? Why do you do it? Let's say you are an engineer. Do you know what equations of state are in chemical engineering? The chemical engineers know. Okay.
เราเองอะ
So, equation of what is an equation of state? An equation of state is some equation, for instance, for a mixture, for a binary mixture or a ternary mixture, and you say I will put mole fraction of this and mole fraction of some percentage of this, a percentage of that, a percentage of that, and what is the pressure at this temperature? Okay, that's a question a chemical engineer is interested in. You want to make a reactor, but you don't want the reactor to explode, so you would like to know, as a function of composition, what is the pressure. And then you go to some books, and maybe you find a book by Mr. Wagner, and you have these Wagner equations, and the Wagner equation says, okay, the vapor pressure is 3.5 times mole fraction of this, divided by 7 pi, multiplied by blah blah, plus the mole fraction of that. So it's empirical, it's fitted, right? These equations of state, they are fitted, okay? And you may have the problem that you have with all the fits that I discussed a little bit in the beginning that you cannot use for extrapolation. Right? The fit, they are good for the range of variables where you have fitted, but if you go to outside, the fit may be crazy. Remember the example that I showed you? Where is it?
Maybe it's conform your change your boundary condition to prove the equation, right?
Well, I mean, a fitted equation you cannot really prove.
You can just maybe like this,
I mean, a fit is a fit.
maybe like harmonic fit like this.
Like this, right? I mean, it's just a fit. And so the harmonic fit is maybe okay where you have fitted, but not outside.
Not outside of the potential. That's one example.
So remember this one. We said we have some variables. Okay, maybe this is the pressure of a ternary system as a function of temperature. So the pressure increases, but at some point maybe you have a condensation or you make a two-phase system instead of something, and the pressure decreases. Okay, so you have measured this, and then you say, okay, I will find some mathematical expression, and you find this green curve. I don't really know what it is. I've found just some curve. And you say, okay, this is just a nice description of my measurement, and I will use this. But then comes somebody else and says, well, you can do better. You can do this blue curve, and this blue curve, where you see it here from the residual, that fits a little better. So the blue curve would be a better, quote unquote, equation of state. And then you say, okay, all right, let's use the blue curve, and now I have fitted in the range between 0 and 1 of some variable. Let's just go to minus something, or let's go to between 1 and 2. And what do you see? You see that when you are outside the range, they predict completely different things. You know, your equation of state 1 says, oh, when you go to higher something, then the pressure will go up again, and green one says, well, no, it will first go down and then more or less go to constant value. So your fit is useless outside the area where you have fitted. And inside it doesn't make any difference. I mean, inside you can use whatever you want, and outside you have no idea. And so in engineering, more and more people find that these empirical fits are not really what they need, that they need a physical background. They need to understand how to compute the pressure from the physical understanding of the system. Now, what is the physical understanding of the system? The physical understanding of the system is I have molecules of type A, and I have molecules of type B, and maybe I have molecules of type C. And they interact. So I have to understand their interaction, which means I have to compute the potential energy surface. Okay? Does A and B make hydrogen bonds or not? Does A and C form a complex or not? I have to understand this, and all this is given by the potential energy surface. So I have step 1, I have to study the potential energy surface. Now, theoretically, you do by quantum mechanics. Practically, there are also other means, there are other ways you can get information about the potential energy surface. I mean, some experiments give pretty good idea about potential energy surface, but they're very, very difficult. Like cross beam experiment, you take a beam of molecule A and a beam of molecule B, and they scatter. from the scatter, of course, the scattering is because of interaction of the potential energy surface. So from the scattering, you can learn something about the potential energy surface. Very, very difficult experiment. And you learn mostly about the repulsive part of the potential energy surface. Not so much about the attractive part. Because you know your two beams are boom. And at the end, the interaction is usually at high kinetic energy, even if you use very slow beams. And so you feel the repulsive part. Okay, so what I'm saying is you need this microscopic information. Quantum mechanics is one way to get it, and there are also other ways. But we have mostly discussed the quantum mechanical way. So you have this microscopic information, molecule A and molecule B interact such, and the minimum energy is such and such, and the orientations are blah, blah, blah. I mean, all this that you can extract from the potential energy surface. So that's question number one. And question number two is, well, I can study only maybe 2 or maybe 3 molecules, but not more. However, in my liquid, I have many, many molecules, you know, half a mole of this and half a mole of this and half a mole of this. How can I study this? Well, certainly not by quantum mechanics, because I cannot study a mole of electrons. That's just not possible. So I have to find a different approximation, and this different approximation is statistical mechanics. Then I do some simplification, and simplification is I express my potential energy surface. I say, oh, the interaction between this molecule and this molecule, this really looks like a Lennard-Jones, so let's write down some Lennard-Jones expression. So you fit the Lennard-Jones expression, and the Lennard-Jones expression has some advantage. It goes to infinity at very short distances, and you know that this is correct physically, and it goes to 0 at very long distances, and you also know this is correct. So you can, in some way, trust the Lennard-Jones potential. You know, if you fit, for instance, I could fit a polynomial. But the polynomial is not really good, because, for instance, if you look at the polynomial, if you have odd powers like x3, x5, yeah, and then at very large distances it diverges, it becomes either positive or negative. It does not go to 0 at very large distances. So, you know, polynomial would be not such a good guess for fitting. So, fitting functions like Lennard-Jones is good, because they have the correct behavior at the limit. I mean, they will not do crazy things like this. Okay? So this is your step number 2. You try to express your interactions by some mathematical functions. And then, and this is the part that we have not discussed, or we have just started discussing, we will study how many such molecules behave when they are put in some specific condition. Like when they are given a certain total energy, and when they are restricted to some volume. And this is like I showed you, right, this is this business here. No, here I have it doesn't work. Probably I should remove some of this. Huh? No, it remains small. What does it remain small? Froze. Somehow it died. It does not like the other screen.
engineering like handbook, there are like many tables to see the properties of the substances. Is that from quantum mechanics?
I mean, probably most of the thing you find in let's say handbook of this and that in chemical engineering, this is still fit. It's fitted data. So people have made measurements and I mean, like this guy Wagner, he published hundreds and hundreds of state equations for many different systems, and he just measured and fit. So measure, fit, measure, fit, measure, fit. But sometimes you want, you know, in chemical engineering, sometimes you want to do something new. And you will not find the state equation in the book. And then the question is, what do you do?
Create new.
Okay, one way, of course, is you do the experiment yourself and you fit yourself. That's one possibility. But you know, it can be quite cumbersome, because if you do the experiment, you know, you do the experiment for one composition, and then the question is, of course, for instance, you want to change the mole ratios, right? You want to have a binary or ternary system, and you want to study all mole ratios. Well, then you have to do many, many, many experiments, and the question is, could you possibly maybe not do any experiment at all, but do fewer experiments so you understand the trends? You understand, if I add A, then something would happen, or if I add B, I will have a phase separation, and the upper critical point will be such and such. And so in engineering, I think these things can be used to supplement existing knowledge. And I mean, a couple of years ago, actually I can show you the results. I studied with chemical engineers two-phase systems, and they were interested in liquid extraction. And of course, when you do liquid extraction, what you need to do is pull one molecule from one phase into the other. Now, between the two phases, there is a layer. And nobody really knows how this layer looks like. I mean, do you have molecule A, nothing, B, or is it continuous? Do you have, in these interfacial layers, even if the molecules are not miscible, in the interfacial layers they must mix.
Yeah.
Because you must go from one to the other. How is this? How many molecules, how deep, how thick is this interfacial layer? You can measure a little bit, but not so. So this was a question that some engineering friends one day came to our lab and said, we are fighting with this problem and we don't really know, and what can we do? And then we said, well, we can write a PhD thesis about this. And that's what we did.
Oh.
I have it here because I like to show it to engineers. So this is typical problem like interfaces that you cannot do with state equations, right? Cannot do. So this would be another justification why you should study these physical models where the interaction really have some sense. You know, it's not just a fitting factor, because you can study so you have AB, you can study the A liquid. And if you are happy with the A liquid, it has the right viscosity and the right diffusion coefficient and blah. And then you study the B liquid, and then you can make mixture, and you can study the phase diagram. And when you have that, then you can say, okay, I will go into the region where they are not miscible. So I basically choose my mole fraction and my temperature such that I'm in the miscibility gap, where the two liquids are not miscible. But I mean, if I put A molecules and B molecules in my system, I will have demixing, exactly like in reality. And between these two demixing, I will have the phase separation. And now I can look very carefully at the phase separation. How does it look like? How many molecules? I mean, so we had a system. So we made some big box. And here I put A molecules. And here I put B molecules. So how is it in between here? Now, first of all, you know that it's not exactly like that because you always have partial miscibility.
Yep.
Right? You know, when you do this, I would tell Ajahn Adrian that you don't know. You know, when you do this, you have the upper critical point, and then you have this lever rule, and then if you are here, actually you have a mixture with this composition and this composition. Remember this? Chemical engineers, I mean electric engineers probably never heard about this, but chemical engineers should really know that. So basically, here I have, let's say here I have the red molecules, here I have the green molecules. So here I have maybe a few green molecules in the red, and here I have maybe a few red molecules in the green. And then the question is, how does it look here? I mean, you know, of course, there will be fewer and fewer red molecules and more green molecules. But how does it look? And so you can make a profile. So you let's just get a different color. So I will plot the concentrations and the concentration of red. Of course, it's not 100% here because I have some green, but the concentration of red, you know, will go something like this. And the concentration of green. Soon we will not have any electricity anymore.
Oh no.
Oh my, okay. I went below zero, it's not good, so let's remove this line. And the concentration of green will be something like this. And the question is, this region here, this is what the engineers were interested in. How big is this? Is this very steep, like, or is it very soft, like I made here, or maybe even softer? And this no state equation will ever tell you. For this, you really need a physical model. Okay? So what do we need to know for this? Well, we need to have the potential energy surface for red. I made it green, but okay. Let's use blue for potential energy surface. So we need a potential energy surface for red. We need a potential energy surface for green. And we need a potential energy surface for green-red. And if we do all this correctly, and we use some condition of temperature and mole fractions. I think we used 50-50, but I'm not sure. We will get phase separation, and if we get phase separation, we can study this interface. So this is a typical engineering problem that was studied by such simulation methods, actually by molecular dynamics. That's a very, very good thesis. I mean, absolutely first grade on Technische Hochschule Darmstadt. And the guy who did this thesis, he is now a big director at some chemical company.
Oh.
Wacker Chemie, if I remember correctly. So we think you will more and more find such things in the literature. And this is why we think you should understand these modeling and simulation. Okay, let's think of Ajahn-Montree. What's Ajahn-Montree's problem? Well, Ajahn-Montree's problem is that he has a solid here, maybe graphite. Okay? So no red balls in here, just graphite. But outside he has, well, maybe he has lithium ions. And maybe he has water. So let's say green is lithium ion and this is water or some other solvent. Okay? And the question is, well, what he would like to do is he would like to have charging, discharging processes here. So somehow his lithium, that must come close to the graphite, so some electron exchange process can take place, or some charge transfer can take place.
Yes.
How does it look? How close can this come to the graphite? What happens if maybe the graphite is not perfect? Maybe there is a hole in there. Is it good because the lithium goes in here? Or is it bad because the lithium remains stuck and cannot get out again? Can you answer this question? Well, nobody can. You have to do the calculations. And there was also, I mean, on such surfaces, there was also a PhD thesis a couple of years ago. The guy's name was, his little name was Payou.
Oh.
You know Payou, famous Payou? Okay. So Payou's thesis dealt with things like that. And I think he also did experiment. But part of the thesis is simulating interfaces, but not liquid-liquid interface, simulating solid-liquid interfaces. And again, you cannot do that with state equations.
Yeah.
So this is the motivation why we in Vistec think that you should learn this.
Yeah. So something that we learned today, like the vibration of bonds, that's the like basis. Is something that we use molecular dynamics for. Right?
Well, if you just want to study the infrared spectra, usually it is enough to use the harmonic approximation, and then you do the normal modes and you don't need the molecular dynamics. But sometimes it is not good enough, and then indeed you have to do, I can also show you, maybe this works now. It's still not working. Let's try. What's it called? Let's see whether the bird works better now. Okay, I will make it nice. If I can find my mouse. Yes. So this is again, you know, my 500 something water molecules. And you know, if I let them move, you see nothing. You really see nothing. So maybe we can just select one molecule, not look at all, but just select one molecule. So let me try to do that. Okay, here I've just one. Okay, here I've just one molecule, and now we can see a little better how it moves. And now, of course, your duty is this complicated motion. You have to analyze it. You have to say what is translation, what is rotation, what is vibration. And that's sometimes not so easy, but you can see that the most visible part of the motion is sort of these rotations. But if you look at the OH distance, you see it changes a little bit, and so there's vibration. So you see a molecule in such a liquid that does not move very much, that just sits there and rattles around, and only in some instances it is able to push a neighbor away and then move for a slightly bigger distance. I mean, if I switch on all the other molecules, I mean, you see nothing. Okay, and this is why you have to do statistics. I mean, of course, you say all molecules are equivalent. So I can look at this molecule, but I can look at any other molecule, and they are all equivalent. So I can make averages. This is the point of making averages, that you say. No molecule in a liquid is special. Right? They're all equivalent. And this is what we will do next semester. We will probably come back to this picture, and then, I mean, there is one more thing, or one last thing I can show you. And this is just because the graphics is so nice. I don't see. So here I draw as points everywhere where the molecule will go during my 2000 configurations that I sample. So You see, it does not go very far. I mean, see, the molecule is about, well, OH distance is 1 angstrom, you know, so your molecule is maybe 1 point, let's say 2 angstrom, something like that. And you see, it does not move very much away from its initial position. It just rattles around. Now we could try to plot the neighbors. Let's say we can plot the neighbors. This is where the neighbors go. So now you can see how the neighbors behave. All this you can then analyze. For instance, you can ask, makes hydrogen bond with the neighbors, but how long does a hydrogen bond live? You know, what is the lifetime of a hydrogen bond? Minutes, seconds, hours, days, picoseconds. It's important in biology, because biology has a lot to do with making and breaking hydrogen bonds. So you want to know how long they exist. Okay? And the answer is, you don't really know, but a few picoseconds. In a liquid. In a solid, I mean, if you have a crystal with hydrogen bonds, then of course the lifetime is much longer. So all these things are you know, well beyond what you can do with empirical equations. And if you want to understand all these things, you must really understand how the molecules interact. I mean, what are the forces between the molecules? What are the energies between the molecules? Otherwise, you will never understand this. So here I plot a couple of hydrogens, which and not the oxygens. So see, there are 2 hydrogens, but the oxygen is not with them, and this is just because maybe if I use a slightly larger value here, it will plot also the oxygen. Yes. So this is a water molecule with its neighbors.
When we change the number of molecules, does potential energy surface is changed or not? The number.
Not in our approximation. In reality, maybe. In reality, maybe. But in our approximation, in particular, when we use this pair potential approximation that Michael has discussed, the potential energy surface itself does not depend on how many molecules are there. But it could be, it happens because of polarization, right? If I have 2 atoms or 2 molecules and they interact, and then the potential energy surface is something. But if I have maybe an ion sitting there, you know, big negative charge or positive charge, maybe it will polarize this molecule, and then the potential energy surface will be different. But that we neglect, that is not in our model. But more and more people make models now where this is incorporated. And then you cannot do pair potential, then you have to do more sophisticated representations of the potential energy surface. I mean, the pair potential representation is really the simplest representation of potential energy surface that you can think of. I mean, quite surprising it works so well, actually. Many people think it should not work, but it works. So our approach is really like Lego approach, and you know, one Lego stone does not change if you put another Lego stone on it. Okay, more questions. More questions, more questions. Oh, you can spend hours playing with this.
Like, yes.
I mean, I just actually okay, the configurations I made many years ago, but the software that does all this, that's free. That you can download. And,
What is the software?
VMD.
Oh,
Software is called VMD, and you can download for Linux, for Mac, Macintosh, or something Apple, and you can download for Windows, and it installs very easily. And they
VMD.
VMD.
I use that one.
You use that? Use VMD?
Yeah, because my project is work use the MD for biological.
Okay. Yeah. Actually, VMD has quite nice features for biology because it knows about amino acids, so you can.
Yeah.
So you don't have to say amino acid is N plus blah 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 blah. It knows. Okay, so biologists like VMD very much.
Yeah.
But there are others. I mean, other people use other software, and then
I have another one is Discovery Studio.
okay, but that costs something. That's not free.
Yeah, it's not free.
But people who do crystals, they like ones called JMOL. JMOL
Yeah.
is good for crystals because it knows about crystallography. So JMOL takes crystallography information directly, which VMD cannot do, and so. You know, these programs, they have been developed by different communities and they have
Yeah.
different interests. And so, there's one, Molden or something, it's also called, I think Molden is also,
Yes,
also quite popular.
that's free.
It's also free, yeah.
Yeah.
And then there's the one by Schrödinger, what is that called? Okay, there are many.
The hair and
Yeah.
Goddard and hair. Jaguar heißt es.
Jaguar, genau, Jaguar. So looking at things, especially for chemists, just looking at things this does not prove anything because one molecule means nothing. You have to look at all molecules, but this gives you ideas. I mean, you say, okay, look at maybe the mechanism for breaking the bond is such and such, and when you have this idea, then you can make the statistics that you need, and we will learn next year how to do that. So this is more to look at it, to play around with, and to get ideas.
so we can just maybe study some complex diffusion based on this.
Yeah. I mean, the diffusion pathway, this would be these points that I showed to you.
Yeah.
This is the self-diffusion of the molecule. And unfortunately, I don't have enough configurations here to really show, but you will see that in water, the self-diffusion pathway is, you know, I take this molecule and then it, but then suddenly they, so there's some sort of jumps. I mean, it rattles around and then suddenly it jumps. And rattle, 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 and jump. And rattle, 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 and jump.
Yeah.
And I will jump away, so
Okay.
You.
Is it already time? I have no idea what's the
Yes,
time.
it's for.
Oh, 4-9. 4-9.
4:09. Okay, so more questions, or shall we adjourn until tomorrow?
Depends on.
มีใคร
I know they have big discussion back there.
มีใครมีค
Have you come to any conclusion?
สี่แล้วทุกคนสี่แล้ว
Okay, let's go.
Let's go.
จูเนียร์
ถามเลยนะ
multiple expansion คืออะไร
เรามีถามเธอด้วยล่ะ
จ้า
Okay, so tomorrow at 1 o'clock, I think paper we have here. Yes, but that's
ข้อสอบให้เขียนบนกระดานแล้วก็ให้เราไม่รู้เดา
เป็นไปได้
พี่คิดว่าเขาอาจจะเขียนคำถามแล้วให้เราตอบแบบเขียนตอบในกระดาษ
จีนนะถ้างั้นนะ
that's all old.
เห็นไหมใช้กระดาษรียูด้วยเห็นไหม
ใจเย็นไม่ดีไม่ดี
Okay, so I will bring some paper tomorrow. Salim Tim will bring some paper.
เยี่ย
I thought this is new paper, but this is just
อ๋อ yeah
old stuff.
also is that free
Okay,
พี่อธิ
so
บาย
I
ที่
can stop these
คอน
molecules.
เทนเชียลของเธอนะคะ It's so satisfied
ฟังมืดมากเลยอะ
มันคูลยังไงอะแบบเป็นทริคก็คืออันเนี้ยคือฟอสกับสเตทของดี
ไม่ได้แบบลงตัว
แบบคอมแล้วนี่แบบใช้
คือไม่ใช่ทั้งหมดนะ
เอาใหม่ตั้งแต่ปีหนึ่ง
อ๋อ
ไม่แต่ว่าอันเนี้ยไม่เหมือนแบบ
เพิ่งเห็นแล้วอ๋ออันนี้อันนี้คือ
แต่
ใช่
คนเดียวที่ไม่ได้เรียน
คอลัมน์
ใครไม่ติดก็เรียน
ผมไม่เป็นแล้วเหมือน
เรี
เดิ
ยน
ม
หมดเปิดเพราะว่าอาจจะมีแค่คิด
แล้วก็บวกกันก็ได้ปิดที่
ปีหนึ่งถึงปี
สี่
สี่
ที่หนึ่ง
จบกันสี่สิบ
เราเก็ตแต่เราเลย
ส่วนที่นี่ไงขายต่อไง
ไม่ได้เรียนในลำปี
ขายต่อนี่ขายต่อขายต่อ
ไม่แล้วค่าเนี่ยขายก็คือมันเป็นค่าแบบมี
ฉันเขาขายกัน30
แต่เองคุ้มมากแล้วค่อยมาคุยกันนี้
ขนาดมึงนอน
คือมันต้องขอรับเรื่องกัน
อะไรฉันเลยเหรอ
ไม่จำเป็น
แต่ว่าที่เราคุยกันนี้มีได้เลยก็คืออันนี้อ๋อคูณเลขตัวเท่านี้อันนี้คูณเท่านี้ใช่ไหมอ่ะแล้วทำไมอันนี้ไม่มีแค่เดียวกัน
ก็คือโพซิชันอันนี้มันคือโพสต่อ
มันคือโพสต์ต่อแต่จริงๆมันไม่ได้มีแค่นี้มันมีอีกแต่
แต่
ว่า
ว่า
เขายกตัวอย่าง
ไอตัวไหนที่เป็นท็อปลิงก์มันคือจะขึ้นกับ2แฟกเตอร์ขึ้นกับจะเป็นอย่างนี้จะอ้วน
อ๋อ
ไหนที่บอกว่าเป็นสองแฟกเตอร์แบบที่คุย
อ๋อ
ไออาร์
มันมีสองโพสต์
ซีรีส์นั้นเก็ต
ใช่ไหมอันนี้มันมีโพสต์เดียวก็คือมันขึ้นอยู่กับไอการเกิดของมันนี่เองอันเดียวแต่มันพอเนี่ยมันเป็น
เชน
ผลของสองไวเบชั่น
มันหลังเซียวีแคน
ไม่โดน
แคนแอนนี่ฟอร์
มันควรจะเที่ยวเลยนะคะของตัวเองว่าสองอัน
ตอนนั้น
ยากมันคืออะไรนะจุเนี่ยไอ้วิ่ง
ก็แค่เป็นโพซิชันในที่ที่มันเกิดผ่านที่
เมื่อไหร่มาก็เยอะ
ตัวเป็นตัว
ระวังเชื่อสั่ง
ว่าสีน้องต้องเป็น
คือกูไปไหว้แล้วแต่ถามไปไหว้
เอาอ่านเด็กกูแล้วไม่รู้เรื่องอะ
มึงในเทคมันก็ไม่มีนะ ในเทคมันก็ไม่ได้จะมีหมดนะ
ถ้าเราแบบมันเป็นตัวเอนจิเนียร์มันเป็นรับชาเลยจ้ะแบบ
แก้ตัวไหนก็ศึกษา
เอาดึงมาเฉพาะขนาดเดียวในการ
ใหญ่
ใช่